Today we're continuing our discussion of logistic regression, and last time we didn't talk about where to get the logistic regression weights. That's what we're going to be talking about today. So just to remind you, this is the form of logistic regression. We have these weights, and we take, for a given observation, the dot product of that observation times the weights, and then that gives us a value that we feed through a logistic function that gives us a probability of a label given our data. And it's used for lots of different things: spam detection, ad placement. It's a huge workhorse in machine learning. What we didn't talk about last time is where these betas come from, and how do you learn them from a bunch of examples of x, y pairs. Okay, so to do this, we need to talk about the objective function for logistic regression. The objective function is what we're trying to maximize. And the objective function is a function of your weights for logistic regression and your data. And we want this number to be as large as possible. This number represents the probability of our labels given our data. So this is a sum over all of our examples of the probability of each example's label given its data and the weights. And so this is just putting it through the logistic regression function. And here you have the numerator and the denominator. And this gets broken apart because log of x over y is equal to log of x minus log of y. And the x is disappearing from here because log of x just equals x. Okay, questions thus far?
Okay, I didn't see the y in the latest slides. I mean, yeah, I didn't see y.
Yeah, so y can either be 0 or 1.
Mm-hmm.
And so this is basically saying, is this the correct y or not? And so if you have y equal to 0, that's a different value than if you have y equal to 1. And so this is just plugging this in here depending on the case, whether it's a positive or a negative example.
So is this a kind of trick?
A little bit. So think about it this way. If y is 0, then the numerator is going to be this. Mm-hmm. And what's log of 1?
0.
Yeah, so when you have a 0, this goes away. And when y is 1, what's the numerator going to be? It's going to be exp of this. And so this is going to be 1 times this. So it just stays.
Oh, okay, I see.
Yeah, so it's a little bit of a trick, but hopefully not too tricky. Good question. Thanks for keeping me honest, as always. Anything else?
I don't think so.
Okay, all right. Thank you very much for pointing that out. Okay, so one nice thing about the logistic regression objective function is that it's convex in terms of beta. And so you can think about the surface as a function of beta, and it looks like this rather than like this. So this is good, this is bad, and thankfully this is what logistic regression looks like in terms of beta. Of course, beta it's more than 2 dimensions. It's as many dimensions as you have features, but it's a really big surface, but thankfully it's convex. So it doesn't matter where you start in terms of your betas. You can always get to a better place in your objective function that is a higher likelihood, a better job of reproducing these labels if you walk up this slope. Okay, and so the mathematical form of this is the gradient, which is the multidimensional analog of this derivative, and so that's what we want to do. Okay, so the basic idea of gradient optimization is that you want to optimize your log likelihood with respect to some variables. So you start off at some point, you walk forward a little bit, based on whatever the gradient was. You take the gradient again, that points you in another direction, you keep going in that direction, you take the gradient again and again. If this were a non-convex function, it's possible that we're missing some optimum that lives over here just because we didn't walk far enough, but thankfully, for logistic regression, we don't have things like this. And so we will end up in an optimal location if we carry out the gradient optimization procedure on the logistic regression likelihood function. Okay, any questions thus far? Okay, all right. So this is the basic idea. So let's now go through the math. What we want to do is, whatever our objective function is, we want to take the derivative of that objective function with respect to our parameters, beta, and then we're going to change our betas based on what the gradient was. And because the logistic regression is convex, this will give us an optimal objective if we do this long enough. Okay, so we needed to figure out what this gradient is, so let's work through that math. Any questions?
No.
Okay, all right. Yeah, so this is not very complicated. It's a little annoying because it's sort of mechanistic. You have to work through a bunch of math, but nothing really all that difficult going on here. Okay, but let's get through this. So to ease our notation, I'm going to define something called pi I. That is basically just this expression, the exp of the dot product over 1 plus the exp of the dot product. And so this will make things a little bit easier. We can rewrite our objective function in terms of these pi's. And so we want the probability of labels given our data to be as large as possible. We'll take the log. We can do that because this is a monotonic function. Then we can just rewrite each contribution to that as either log of pi I if y is 1, and log of 1 minus pi I if yi is 0. So does that make sense?
Why don't you use the objective function as a very start?
So I'm basically doing that. I've just rewritten it slightly so that the reason that I rewrote it is so that when I take the derivative, it will be a little bit nicer. Oh. So I'm rewriting it slightly so that the derivative becomes nicer in a second.
Oh, okay.
Excellent question. Yeah, you're right. So this is functionally equivalent to the objective function that I wrote earlier. The only difference is adding in this pi I so that we'll have nicer derivatives.
Oh, okay.
Okay, so let's then apply the chain rule. So if you take the derivative of this, if y is 1, it's just, so we had log of pi I, so that's 1 over pi I times whatever was inside before. And then if y is 0, then it's 1 over 1 minus pi I since that was inside the log. And then we have a negative because it was 1 minus pi I inside. Make sense?
I see a summation symbol here, so you consider all the samples, right?
For the moment, so that will change in a little bit. Yeah, but for now, we're taking all of the data, so this is just the whole darn thing.
Oh, okay.
Okay, and then if we can compute the derivative in those two cases. So it's pi I times 1 minus pi I times whatever the value was for a particular feature. Mm-hmm. And then we can merge the two cases, and so this is why I wrote it like this. You can then write the derivative as yi minus pi I times whatever the value of the feature was. Okay, so, and just to make this absolutely clear, this is a gradient. So there's going to be a j for every feature and an I for every example. So the overall gradient is going to have something for every feature. So there's going to be, if you have x1 to xm, there's going to be a delta beta 1 up to beta m. Okay, everything cool so far?
Yes.
Okay, so now we have this gradient that we've written down for all of our dimensions. And then the update step that we're going to do, because we want to have the maximum likelihood, is every time we're going to add in to our original weight vector whatever our gradient is. And so these are vectors. So the gradient is a vector, as you can see here, and the weight vector is a vector. We're going to take the dot product of this with our observation, so we just add in whatever the gradient was to get our new value. So this is our gradient step. Okay, so what we haven't talked about is this guy here. So this is the Greek letter eta. And so the eta is just representing how big our step size is going to be. How much are we going to change in every iteration? Okay, so first, before we talk about that, I want to be sure that it's clear why we're adding. You can do either gradient ascent or gradient descent. And so if you're doing gradient ascent, you add because you want higher values of your objective function. And so then you add. If you're doing gradient descent and you want lower values of your objective function, you subtract. So it depends whether you're trying to optimize in big ways or small ways. Make sense?
You mean if I want to have a decent version of this, so this will change to minus symbol?
Yeah, that's right.
I think the plus symbol here is just it's just a convention, because if you want to go down, your derivative will be minus, right?
Well, the gradient will tell you the direction that you're moving, the direction that it is going, and so it does matter if you want to follow the gradient towards larger values or move away from the gradient.
So if we want to do the descent, we still have to change this plus number to minus.
Right. Yeah.
Oh, okay.
If you think about the gravity analogy from physics, if you're on a hill, then gravity is pulling you downwards, and so you can either move against gravity or move in the direction of gravity.
Oh. So if the derivative is minus, but we want to the maximum of the objective function, so we still have to use the plus.
Yeah.
Oh, I see.
And so eta is the step size. It must be greater than 0. Unless you want to flip the direction that you're moving along the gradient. And so I also want to mention that there are more complicated ways and more sophisticated ways of doing gradient optimization. There are things called gradient descent with conjugates, and that usually works better than a simple gradient descent, but it's harder to implement. It's sort of outside the scope of this course. You should check it out if you're doing this more seriously. Okay, so let's talk about choosing the right step size. So if you choose step sizes that are too small, then it will take forever for you to get to where you want to go. And so you might take little step, little step, little step, little step. And then you waited 30 hours and you think that you've gotten to a good place, but you really haven't moved much at all. If you choose step sizes that are too large, you could just ping pong back and forth and never hit your true objective. So you're just going on either side of the optimum and not really getting to where you want to go. There are some other issues. So when do you stop your optimization? You can do a couple of things. One, you can look to see if beta doesn't change very much. That usually works well. Or if your objective function doesn't change very much, that also works well. A lot of people are lazier and just do it for some number of iterations. That could run into problems. One other problem is you might not have a well-defined maximum. Your objective function could look something like this, where it just slowly tapers off and just keeps getting bigger and bigger. And so if your objective function goes linearly with your beta, or monotonically with your beta even, then you may not stop. You may not reach a maximum. And so one way of addressing that is changing your objective function so that you penalize overly large weights. And so this gets back to the question that you asked last time about are there ways to add priors in logistic regression. This corresponds to a prior over the weight values, that you want to prefer weight values that are smaller. The probabilistic interpretation, which is discussed at fair length in the book, is that you're assuming that your beta distribution comes from a Gaussian, and this looks something like the log probability of beta coming from a Gaussian with mean 0 and unit variance. So if you take the log of this, that looks something like a quadratic. The mu here is a parameter that controls how much you care about maximizing your likelihood, which is this term, versus having small parameters. So if mu is 0, then you're doing the standard unregularized updates, but if mu gets bigger, then it's saying that you must absolutely optimize for smaller weights. Okay, any questions?
No.
Okay, all right. So you asked the question, in our objective function, we have the sum over all of our observations of these individual terms. Why might that be a bad idea? And so that was an excellent question. And sometimes our data sets are really big. And we can't fit all of our examples into memory. So let's say that we're Google and we're trying to do a spam filter, and we have all of the emails that have ever been sent on Gmail. That won't fit on a single machine, nor will it fit on most clusters. Can we still solve this sort of problem even if we can't fit all of our data into memory? Or maybe our data are inherently streaming some way. So maybe we're Twitter, and we don't keep track of all of the tweets over all time. We might just only look at the most recent in days of data. Can we still have an algorithm in that case? So if we can't get all of our data into memory, we can't compute the true gradient. And so the true gradient, we can think of this as an expectation over all of our data of the gradient of a single observation. So this is just a different way of writing the gradient. Do you believe that this is a gradient?
I think you should explain this equation because I didn't get it.
Okay, all right. Okay, so the expectation. So let's define this notation. So the expectation of some function is either the sum or the integral over all of the things in this universe of p of x times f of x. So you can think about this as sort of like a weighted average. So you're weighting the average of this function, whatever this is, by how likely the inputs to the function are. So if so this is the definition of expectation, and what do we do if we have an expectation over observation? So what does that mean? This means that we have some universe that we're getting examples from, and what we want to do is we want to consider all of the things in our universe. And so this is what this expectation means. You have an expectations over all of the things in the universe, and then we take the average of that. And so what is it that we're taking an average of here? So this is the gradient of our objective function with respect to a single observation. So if you average that over all the things in the universe, then do you believe that that is equal to the gradient with respect to the true data set?
By saying universe, you mean our data set, right?
Well, so not exactly. So to be a little bit pedantic, when I say universe, that's something larger than the data set itself. And the universe is everything that could exist, everything that our data set could be. So like, let's say that we're doing spam detection. Here the universe is all possible emails. And then our data set represents a very large sample of that universe, and hopefully it is representative.
Oh, so if X is in the universe, it's not in our data set. It's
but it could be. It could be. It's not necessarily in our data set, but it could be.
So in the expected value, this equation, you have probability of X. So did you mean that if X is in our data set, its probability will be 1?
Well, so it can't be, because unless there's only one email. So
there's some to 1.
Yeah,
right?
exactly.
Oh, I see. But if it's not in our data set, it will be definitely 0, right? Or not?
Not necessarily. I mean, you could write some email, and that might have some infinitesimal probability. It might not be in the data set. Maybe you sent that with Yahoo Mail rather than Google Mail, and it just doesn't happen to be in that data set.
Okay, so but I don't get why you choose this form.
Right. So okay. That's a perfectly reasonable response. So one, you might say, you're just playing games with math, and when you actually take the gradient, you use a real data set because you don't have some perfect model of all of the emails that could ever be. You're not God with infinite wisdom. The reason that I wrote it this way is to convince you, hopefully, that any data set that we have is just going to be an estimate of what the true universe of data look like. And this is what we really want. This is perfection. This is what we would do if we could, but we can't, and any data set is going to be an approximation of this. And so if we're going to make an approximation of this true gradient using some data set that is probably imperfect in some way, why not make a further approximation?
Oh, I see.
Okay, so maybe you believe me, maybe you don't. But anyway, let's try to make a further approximation of this. What if instead of averaging over all of our observations in a data set, what if we just update from one observation? So instead of doing an expectation over all of our data, just look at one observation, compute the gradient based on that observation. Okay, so that was sort of the math way of trying to convince you that this isn't a totally crazy idea, that all data sets are an approximation, so why not just approximate it further by using one observation? Okay, so the sort of other way that I'll try to convince you is, let's say that you're trying to get to some location. Let's say that you're trying to get to the big train station in Denver, Union Station, and you want to get there and you don't have a smartphone. So I'll present you with two ways of figuring out how to get there. And let's say that you're starting off here in Boulder and you want to get to Union Station. Option one, you can ask everyone in Boulder, what way is Union Station? So you ask all 102,000 people in Boulder, what way is Union Station? You will get lots and lots of answers, most of them pointing southeast. So some of them are going to be wrong, but most of them will hopefully point in the right direction. And when you take the average of this using the wisdom of crowds, you will get a very good direction to go to Union Station. You could probably walk on that line. You would probably cross some highways on the way there. That would probably be dangerous, but you get a good straight shot to Union Station. But it takes a long time to ask 102,000 people how to get to Union Station. What if you just walked out that door and the first person you saw, you asked them what's the best direction to get to Union Station? And who knows, maybe they would give you the right direction, maybe not, but then you just walk a little bit and you ask the next person you see, what's the best way to get to Union Station? You follow those directions, you go a little bit further, you ask the next person, the next person. Some of those people are going to be wrong, some of those people are going to be idiots, but on average, most people will give you good directions, and you'll spend a lot less of your time asking people questions, and you'll spend more of your time moving. So that's the other argument for doing this stochastic approximation of gradient descent. You just ask one person, which way should I go? So you're asking each data point, what gradient should I take? Then you do that, and hopefully you end up in a good location. Okay, so do you have any reaction to either of those arguments?
No.
Okay, all right. Maybe you believe me, maybe you don't. It is a lot faster than doing the batch updates. So just to work through this math, for a single observation chosen at random from the data set, you have your old parameters, you have your step size, and then you have...
Is that derivative?
Yeah, so this is the gradient with respect to a single observation. So you're just saying, does my answer match my prediction? So if pi I is matches, then you really don't change much. And if pi I is very different, then the feature value, the sign of the feature value tells you which way you should change your parameter. And we'll see a bunch of examples in class. Okay, so this doesn't change too much when we have regularized regression. And so our objective function changes slightly, but then the derivative only gets this additional beta term. Okay, so there are some details that we didn't talk about. So in particular, the convexity of the objective really matters and how close you want to get to an actual answer, and sometimes you can do okay with these approximations if you don't need to be really, really close to the optimal answer. And the best bounds depend on what your eta is, and actually changing your eta over time and making it smaller and smaller and smaller, and adapting it per dimension rather than doing it the same over all of your features works better. Okay, any questions?
Well, you said how close is the sigma? Epsilon, right?
Yeah, yeah. Mm-hmm. Yeah, epsilon.
Yeah. Is that the difference between the true answer and your answer from the algorithm?
Yeah, exactly, yeah.
But
right, so we can say the beta that you found and beta optimal.
Oh, but you also said it's very hard to compute the real.
Oh yes, yes, and so this is just a theoretical guarantee. So right, we don't know what this is, but some smart people have worked out the theory behind how close you can get to the optimal answer.
Oh, okay, I see.
Good clarification. Okay, so that's it for logistic regression. In class, we'll answer your questions, so be sure to come to class with your questions. We'll work through some simple examples, and after that, you should be prepared for the logistic regression homework, where you will implement logistic regression. All right, thanks, and see you then.